Not yet. Okay.
All right, so welcome everyone to the GeoDevs seminar. So today we are very happy to have Federico Zerbini, who will speak about the periods of string theory amplitudes. Thank you.
Okay, so thanks a lot for inviting me to this very nice seminar. Yeah, I would like to talk about something related with physics. I have a mathematical background, but I've been fascinated by some problems coming from string theory, notably. So I'd like to try to share my enthusiasm with you. And there's a lot of periods going on, and I hope you'll enjoy that. So the outline of my talk is the following. So I will start with some motivation / introduction to the physics behind the mathematical problems. And then, well, it will turn out that the relevant geometry behind all this is that of Riemann surfaces. And so I will start telling you something about genus 0, then genus 1. And in both cases, I will talk about some non-trivial notion, relatively new in this case, notion of periods. And then at the very end, I will also mention something about higher genus. So this is rather an overview of these problems coming from string theory. I'm not going to go into any specific result, and at the end you can ask me something more precise if something is interesting more than something else. So let's start. Okay, so probably most of you know that it's very important in modern physics that we can build particle accelerators and make experiments, because these experiments have been the most astonishing confirmation of quantum physics in the last years. So here I've reported a picture which is related to the discovery of the Higgs boson at LHC at CERN. So you can see these little black dots. So these are the data collected by the Large Hadron Collider. And then you can also see this blue line here, this curve. So this is what is called the background curve. And it's obtained by theoretical predictions using the standard model without the Higgs boson. And here you see that there is this bump, and that is related to the fact that there is this extra particle. So the topic we discussed today is how does one construct this blue curve? So how does one get this background curve? It turns out it's not easy. I mean, of course, you need the particle accelerator to collect the data, but you also need to compute the theoretical prediction from quantum field theory. And to do so, you have to compute a lot of scattering amplitudes. So what are scattering amplitudes? So in quantum physics, whenever you have particles, let's say two particles that interact, you cannot really tell what's going to happen. So suppose you find your particle at a certain time here and here, so in a certain point in space, you can only predict what's the probability of finding them that time and that place. And this probability of interaction is what we call the scattering amplitude, because this is what is called a scattering process. And to compute them, or let's say to approximate them very precisely, what you do is to follow Feynman's original approach, which is still the most effective method to do so. So it's a perturbative approach. The idea is, well, you kind of take into account every possible things that may happen in here. Well, you have to build some kind of models of the possible interactions. So it turns out that you can reduce the combinatorics of all the possible things happening to some graphs, which are the famous Feynman diagrams. So these are two examples, and then there is more. Well, the probability of each of these diagrams, so of each of these possible events, is computed by an integral, which is called the Feynman integral. And the idea is to compute a weighted average over all the infinite possibilities that you have. This is not very well defined mathematically, but it turns out it's incredibly effective from the computational viewpoint. So that's how they build these background curves. They compute just a very few number of Feynman integrals, and the simplest one, in fact, the ones like this, or where you have just one loop. So the simple means a low number of loops, which mean particle is created and then annihilated. And by computing just a very little number of integrals, they have a very precise approximation of the interaction they are trying to study. And this is very interesting also for mathematicians, these Feynman integrals, because of the following very simple remark. It's not difficult to see that all Feynman integrals are periods. Well, here, I mean periods in the sense of Kontsevich-Zegier. I don't know how to make this thing go away. Okay, so by period here, I just mean complex numbers whose real and imaginary part are given by integrals of rational functions with rational coefficients over Q semi-algebraic domains, which means that you are taking inequalities, polynomial inequalities with rational coefficients. But later we'll see a more deep definition of periods. Okay, so let me give you a little bit of history of this interaction between mathematicians and physicists on the subject of Feynman integrals. So in the early 90s, two physicists, Broadhurst and Kramer, did some extensive computations of Feynman integrals in terms of multiple zeta values, which are these very famous numbers, which I give here as nested sums. So these KIs are positive integers. And of course, if R is equal to 1, these are just special values of the Riemann zeta function. So the name comes from there. And well, it was observed apparently first by Kontsevich that multiple zeta values are integrals, are iterated integrals, in fact, of the one forms dx over x and dx over x minus y from 0 to 1. And for instance, here I wrote the integral representation of the special values of the Riemann zeta function, which is fairly simple. So this is what I mean by iterated integrals. You integrate x1 from 0 to x2, and then x2 from 0 to x3, and so on. And it's a simple exercise to show this equality. And then you have a more general formula, which is a little bit more cumbersome, so I don't write, for the general multiple zeta values. This means, of course, these forms are algebraic. I mean, they're rational with rational coefficients. And so multiple zeta values are periods. And in fact, they're very special periods. So they're periods of the simplest category of mixed motives, which is that of mixed state motives over Z. I'm not going to talk about motives especially, but it's good to keep in mind where the periods come from. So motives basically tell you what's the geometry behind the periods. And there was a folklore conjecture in the 90s that some people attributed to Kontsevich that tells you that all Feynman integrals should come from this kind of motives, so should have this kind of quite simple geometry. So this was in fact false. This was proved to be false in the 2000s, but only recently people found some more concrete example. And this means that you can find a lot of periods in principle in quantum field theory from Feynman integrals. And we will see something beyond multiple zeta values later. But let me also tell you that this interaction between mathematicians and physicists is particularly interesting for physicists because starting from the 2010s, let's say, computations, algorithms built with using the geometric nature of Feynman integrals proved to be, in fact, faster and more accurate than the ones built by physicists. This was quite impressive and for physicists because they used to think that they're better in computing things. But that explains why there are so many conferences right now that try to put together mathematicians and physicists computing amplitudes. And also let me mention that there is a big program for because for mathematicians also it's interesting, the mathematical structure of amplitudes. There is this big program initiated by people like Cartier, Kohn, and Marcolli that is now carried on by Francis Brown especially and his collaborators to study the motivic amplitudes, so to give a motivic meaning to amplitudes and to study the action of the motivic Galois group behind, which people call the cosmic Galois group. Okay, so this was just to give a little bit of background. What I'm going to talk about is not really quantum field theory amplitudes, which is what I've been talking about so far. It's rather string theory amplitudes. So string theory is a generalization of quantum field theory. So in some sense, what I've said is or should be contained in what I'm going to say now. So the idea behind string theory is that you want to generalize quantum field theory to be able to describe also gravity. And from the particle physics viewpoint, the difference is that instead of representing particles as points, you think of them as little strings, which are in red in this picture. So you have two kinds of strings. So their strings are then unidimensional objects instead of zero-dimensional. And you can have either open strings like here or closed strings like here. So little circles. And when these strings interact, so they evolve in time, instead of creating these Feynman diagrams, so these graphs, they will create some surface, which in the case of open string will have boundaries, which are in black here. And in the case of closed strings, won't have any boundaries except for the strings themselves, which will be boundaries of the surface. Good. So yeah, let me also mention that physically open strings are responsible for gauge theories and closed strings are responsible for gravity. Now, there is some physics argument that in fact allows you to shrink the strings to just mark points. So in the open string case then, what used to be a disk with various kinds of boundary components now is just a disk with one boundary component and string insertion on the boundary. And then you have more complicated topologies. For instance, here you have an annulus with string insertions on the boundary. And in the closed string case, on the other hand, you start getting compact closed surfaces, in fact. So this is a sphere, even though it's not the best picture. This is a torus with one hole, with two holes, and so on. And in fact, it turns out that at least in the closed string case, you can think of this as Riemann surfaces. So you put a complex structure on them, and to each topology, you will associate to compute this. You can think of this as some kind of Feynman diagrams, and to each of them, you can associate a Feynman integral, and the integration domain of these Feynman integrals is the relevant moduli space for the topology you are considering. And so, for instance, in the closed string case, the natural thing to do, to obtain, are Feynman integrals, which are integrals over moduli spaces of Riemann surfaces with mark points. And so you will have genus 0 Riemann surfaces, then genus 1 Riemann surfaces, genus 2, and so on. And you do similar things in open string theory. So that's why the next part of the talk is going to be about genus 0 contributions to string amplitudes, and then I will talk about genus 1 and higher genus. Okay, so let me start with genus 0 amplitudes and with a couple of examples of these scattering amplitudes. So I want to talk about, so these are the Feynman integrals, not really the amplitudes, but rather the integrals behind the amplitudes that compute the genus 0 contribution with 4 mark points. So this 0 and 4 refer to that. For open strings and for closed strings. They're not numbers, they're not just periods, in fact, because they depend on two parameters, S and T, which are kinematic parameters, so they depend on the physics of the problem. And And physicists are particularly interested in the behavior as s and t go to 0 of these integrals. So let me also mention that this open string integral was first studied by Veneziano in 1968, and it kind of marked the birth of string theory. And the second one was considered immediately after by Virasoro. So there are two very classical, very well understood Feynman integrals, and they're also the simplest ones because for physical reasons, you don't get less than 4 strings interacting in Genus 0. Good. So let's take a closer look to this. So I promised you that these Feynman integrals would be integrals over certain moduli spaces of points over certain kind of surfaces. And here you get an integral over the interval 0, 1. Why that? Well, because so this you can think of this circle as just the real line, and by some symmetries that you can exploit in string theory, you can fix 3 of the 4 strings at 0, 1, and infinity. And so the fourth one is free to be between 0, 1 or 1 infinity or 0 infinity, but in fact it turns out you can just fix it to be between 0 and 1 and you get everything. And so that's why you have this integral over 0, 1. And well, this is a very well-known integral. This is just the Euler beta function. So it's well known that you write this as a quotient of gamma functions. And as I said, physicists are interested in the so-called low energy expansion. So for S and T that go to 0, because this will give you back the quantum field theory limit of string theory. And it's very well known that the expansion of this function is given by the following formula, where these zeta of n are just special values of the Riemann zeta function. And in the closed string case, well, you have now, as I said, for closed strings, you have 4 mark points on a sphere, but you can fix 3 of them again in 0, 1, infinity. So you have only 1 point traveling around your Riemann sphere, P1C. That's the integral you've got to compute, and that's the result. This is a less known computation, but it's quite classical too. And the result is the following. So it's very similar from the open one, but here instead of getting all the Riemann zeta values, you just get the odd ones, which some of you probably know are very special. I mean, the even ones are all powers of pi, while the odd ones are conjecturally transcendental and all algebraically independent. So we will see later what's the explanation behind this phenomenon. But let me also tell you that in general, one would like to look at the Genus 0 amplitude for n strings, and one finds numbers, so periods, which are slightly more general than these simple zeta values, but they are always contained in the ring of multiple zeta values. So for instance, here I reported all the multiple zeta values that you find until weight 11 in open and closed strings, where the weight is just the sum of the entries of the multiple zeta value. So I just report the generators actually that you find. Then you will in general find products of these multiple zeta values, but here I just report the new ones. And it turns out that in the open string case, you find something that you don't find in the closed string case. So in the open string case, you actually find all of them experimentally. And in particular, at weight 8, you start finding some irreducible multiple zeta values, which you cannot write as a product of simple zetas. While in weight, for the closed string case, you have to wait until weight 11 to find the first irreducible multiple zeta value, and it actually only comes in this particular linear combination. So here, of course, in the open string case, you get zeta 353 and products of zeta 35 with zeta 3, so of course you get this one. But in the closed string case, you only get this very special combination. You don't just get zeta 353 alone. So something rather special happens for closed string amplitudes, and the first part of the talk is about this phenomenon. I would like to tell you from the period's viewpoint what's going on. So let's go to periods and cohomology. So you probably all know all this, but let me briefly remind you. What's the setting? So we have an algebraic, smooth algebraic variety. You can also think of an affine varieties for the purpose of this talk, and the normal crossing divisor, everything defined over Q. Then you consider the algebraic Durham cohomology of your variety, which for affine varieties is just the cohomology of the complex of global algebraic forms. And the Betti cohomology of the variety, which is just singular cohomology. So these are all relative cohomologies, of course, relative to the normal crossing divisor D. And the Betti cohomology is the singular cohomology of the complex point of your variety with coefficients in Q. And it's a very famous theorem by Grothendieck that extends Durham's theorem to the algebraic setting, that integration of algebraic forms over cycle gives you all the possible functions on cycles. So this gives you a comparison isomorphism between the Durham cohomology tensor with C and the Betti cohomology tensor with C. And if you choose Q basis for Durham and Betti cohomology, then you have a matrix representing the isomorphism, which is called the period matrix, P. And the entries of this matrix will be just integrals of this kind, so integrals of algebraic forms. And it turns out that all of the periods in the Kontsevich-Zagier sense can be obtained this way, and vice versa. So these are the same class of function. It's not a trivial result to prove, but it's true. So you get same periods as in the sense of Kontsevich-Zagier. And importantly for us, there is a version in family of all this. So if your periods depend on parameters, so if your variety in general depends on parameters or your forms, they satisfy, it's a well-known fact that they satisfy differential equations with respect to these parameters called Picard-Fuchs equations. This is a consequence of the fact that cohomology is finite dimensional, essentially. And your period functions then will be some local solutions of these differential equations that will depend, in general, on the path you're analytically continue them on your base space. And so they will give you multi-valued function of the parameter. And well, okay, this you should keep in mind, because now we are going to talk about single-valued periods, and this has to do with the fact that you would like to correct this multi-valued in some sense. So what are single-valued periods? So if your variety X is defined over Q, you can act by complex conjugation on the complex points, and this induces on the Betti cohomology what is called the real Frobenius, so some involution of the Betti cohomology. And you can use this real Frobenius to find some automorphism of the Durham cohomology. So how do you do that? So you tensor with C, you use the comparison isomorphism of Grothendieck, then you use this F infinity, this real Frobenius, and then you go back to Durham by C minus 1. And that's how you define your map, which I call SV for single-valued. And the definition is that single-valued periods are the coefficients of the matrix which represent this automorphism of the Durham cohomology. And if I got this right, but it may not be right, it should look like P minus 1 complex conjugate times P, where P is the period matrix of this comparison isomorphism. Okay, so this seems a rather abstract definition, and it is. Let me first remark, so why are they called single-valued periods? Well, because if you consider single-valued periods in family, so they depend on parameters, they are, at least locally, single-valued functions. So why so? Well, because the monodromy of the period functions are given in the following way. So you have this monodromy acting on the period matrix by just left multiplication by a matrix M. So whenever you analytically continue a solution of your Picard-Fuchs equation along a loop, that's what you get. And your matrix M, it turns out, because you're considering Betic homology, so with singular homology with rational coefficients, that the matrix M is rational. And so if you consider your single-valued matrix of periods and you act by analytic continuation along the same loop, then you get this formula, but your matrix M is rational and therefore real, and therefore this is 1. And you get PSV again. And the second remark is that single-valued periods, because they are fixed, I mean, one can prove they're fixed by complex conjugation using definition, and therefore they're real numbers. And a third remark, which is not very relevant for this talk, is that they're p-adic periods at p equal infinity in some sense. So there are various definitions of p-adic periods. I think you have seen one in this very seminar at some point. So the definition I take here for p-adic periods is the following. So you have crystalline Frobenius Fp, which gives you an automorphism of the crystalline cohomology of your variety. And then you have a comparison isomorphism between H Doram and H crystalline after tensoring by QP. And in the same exact way you did before, so you're replacing the crystalline cohomology with the Betic homology. You induce an isomorphism again over the Doram cohomology, but this time tensored with QP. And the coefficients of this isomorphism are what are called the p-adic periods. So since the real Frobenius you use for the single-valued periods is in some sense a version of the crystalline Frobenius for p equal infinity, then that's why you have this analogy. Okay, now let's try to define single-valued multiple zeta values. So a very important fact for us is that in certain categories of motives, and mixed-state motives are one of these categories, you can construct a single-valued projection that sends you a period, or rather a motivic period, to a single-valued period. I mean, single-valued periods are just defined as the entries of a matrix, but there is no canonical way you can, from a period, associate a single-valued period. So this gives you a canonical way as soon as you are in the right setting. So here you see you associate to this alpha m, the motivic period, this alpha sv, the single-valued period, which is a real number. And well, you have your multiple zeta values, have their motivic version, and then you apply the single-valued map, and you get what you call single-valued multiple zeta values. If you assume standard conjectures, I mean, like the period conjecture by Grothendieck, for instance, then you just have your multiple zeta values, and you apply this SV map to the multiple zeta values, and this is well defined. So this is it's not very hard to prove that, in fact, the ring of real numbers that you obtain is contained in the multiple zeta values. So single-valued multiple zeta values form a subset of multiple zeta values, and in fact, a very small subset. But how to compute them in practice, because this definition is very abstract? Well, the very first definition of single-valued multiple zeta values, I think it was the following. So you have a multiple zeta values, and you can think of them as special values of multiple polylogarithms, which are defined by the following, which are given by these special functions. Obviously, if you set z equal 1, you get directly the definition of multiple zeta values. And there are constructions of single-valued analogs given by combining multiple polylogs with their complex conjugates. So the first one were constructed by, so there is the famous Bloch-Wigner logarithm, for instance, and they were very useful related to hyperbolic geometry, K-theory, and so on. And then the most general version of single-valued multiple polylogs was defined by Francis Brown in 2004. And I mean, here I just report the simplest example. So the log, which is multi-valued, if you find a single valued analog, then this is just the log of the real part. So twice the log of the real part, which is of course single valued. But there is a recipe for all kinds of multiple polylogs, and then single valued multiple zeta values are just the special values at z = 1. So you define them that way. And that's what people do, in fact, to compute examples and to write algorithms. And the first examples you get of single valued multiple zeta values are the following. So the even zeta values are just sent to 0 by this single valued projection, while the odd zeta values are sent to twice themselves. So these are the simplest kind of multiple zeta values. Let's go to the first irreducible one, which is ZL35. Well, its single valued analog is not irreducible anymore, at least if you view it in the ring of multiple zeta values, because it becomes a product of two single zetas. And you have to go to zeta single value of 353 to find something which is irreducible and which is given by this linear combination. So I might have left out a term here, but it's not. It's just a product of zeta values. And well, this is, if you remember the table I gave you before, this is quite interesting because these are exactly the numbers that you get in closed strings amplitude. So you don't get zeta 2, and so you don't get zeta 4, zeta 8, zeta 6, and so on. You don't get zeta 3,5 because it's just a product of zeta 3 and zeta 5 that you already have. And you start getting something new in weight 11, and this is precisely this linear combination of these two irreducible multiple zeta values. And so, in fact, things went the other way around. So physicists found these numbers, and as mathematicians, how do you explain these numbers? And then Francis Brown came out with this theory of single-valued multiple zeta values, which explain the numbers you find in closed string amplitudes. So the conjecture, obviously, at that point was the coefficients of closed string amplitudes are single-valued multiple zeta values. And here's the state of the art right now for Genus 0. So it was proven already in 2013 by Terasoma and some physics collaborator of his that the Taylor coefficients of the open string amplitudes for any number of strings n are multiple zeta values. So this is proven with some standard techniques. But it was more hard to prove the closed string analog of this theorem, so that the Taylor coefficients of the closed string amplitudes at Genus 0 are single-valued multiple zeta values. And there are 3 different proofs of this, all found in 2018. So one is by myself and Pierre Vanov, one is by Francis Brown and Clément Dupont, and one is by Oliver Schlotter and Oliver Schnetz. But the proof by Brown and Dupont provides even more. So they actually proved that there exists a motivic amplitude in some sense, AM0n in Genus 0, such that if you apply the period projection, so to complex numbers, you get the open string amplitudes, or rather its Laurent expansion. And if you apply the single-valued projection, then you get the closed string amplitudes. So they both come from the same motivic object. You just apply, they're just 2 different realizations. And well, this also implies that if you simply naively apply the single-valued map on the multiple zeta values, which is not quite a map, but conjecturally it is, 2 single-valued multiple zeta values, term by term, in the Laurent expansion of the amplitude, you should get the closed string amplitude. And that is precisely what happens, for instance, in our first example of 4 strings, because you have this Laurent expansion here, this Laurent expansion here, and if you apply term by term the single-valued projection on the zeta values, well, the zeta of 2n are going to disappear, the even ones, and the odd ones are going to be multiplied by 2, which is precisely what happens. And so, well, this is all explained by the theorem of Brown and Dupont. So we have this very impressive and very complete picture of the mathematical structure of genus 0 string amplitudes. And so the next obvious thing to do is to go to genus 1 amplitudes, which are therefore related to, at least in the closed string case, to elliptic curves. And we will see that in order to explain how to generalize the mathematics of the genus 0 case, we will have to say something about periods of fundamental groups, which is something that was discussed less than a month ago in this seminar by Malu. Okay, so let's start with a first overview on the kind of objects or functions that you get in string theory. So in genus 1, you have again this A, which is the Feynman integral that you want to compute of genus 1. So you have 1 here and n here, which is the number of strings that you consider. And then here it could be open or closed. And again, it will depend on some kinematic parameters. And again, you will want to study the asymptotic behavior as these parameters go to 0. But the difference here is that at least in the closed string case, so this equality is true actually only in the closed string case, this can be written as an integral over the moduli space of elliptic curves, so of complex toroid with one mark point, of something which will depend on the complex structure tau of the torus. And it is quite mysterious, in fact, in string theory, how to compute this whole integral. So we will only focus on the integrand at genus 1. At genus 0, there was no integrand and integral because the moduli space is just trivial, M03. But here you have something non-trivial. You have a complex structure, tau, and therefore, instead of finding numbers, we will find functions of tau. Good. So in the open string case, if you can expand these functions of S and tau in S, so S goes to 0, and you want to study the Taylor coefficients of this expansion. And it turns out, so this was demonstrated by Brodel, Mafra, Mattes, and Schlotterer, at least in the 4th string case, I think, that the coefficients are given by iterated integrals of one forms defined in the following way. So this seems a rather complicated definition, but so this is just this is not so complicated after all. This is just the Riemann theta function, the odd Riemann theta. So so this function here, this quotient of theta function is sometimes called the Kronecker function. It was already studied in the 19th century. And you can treat this alpha as a formal variable and expand in alpha. And the coefficients of this expansion are functions of z and tau. And it turns out that the Taylor coefficients are iterated integrals of these one forms. And let me mention that these are iterated integrals in the variable z. And they will be therefore functions of tau. And they are called, for reasons that will be perhaps more clear later, elliptic multiple zeta values. So these elliptic multiple zeta values were introduced not long ago by Enriquez, I think in 2013. And we know many things about them, so we can consider the structure of open string amplitudes in genus 1 quite well understood. So one of the things we know, for instance, is that they have a Q expansion, so they're functions of tau, and if Q is e to the 2 pi I tau, so we can expand them at the cusp. And the coefficients of this expansion, quite remarkably, are multiple zeta values. So if you take your favorite modular form, for instance, an Eisenstein series, and you expand this with a usual normalization, then the coefficients will be rational numbers. But here there will be multiple zeta values, which is quite interesting. And the second observation is that they can be written as iterated integrals of completely different kind of objects. So here I mean iterated integrals over tau, not over z, of Eisenstein series. And so in this sense, they are kind of iterated Eichler integrals of Eisenstein series. And this means that they are related to a whole different topic, which is that of periods of modular forms and the periods of the modular space M11. But this is kind of a happy accident. You get, in fact, you just get a very little subset of the iterated integrals of Eisenstein series. And so this is not very relevant for us today. And what about closed strings? Well, closed strings are more interesting in the sense that you find new modular forms which are not known in mathematics. So you have these real analytic modular invariant functions d gamma of tau, where gamma is a graph. So they're, let's say, combinatorics is related to that of graphs. To each graph, you associate a modular function. So that's the most natural name that physicists came up with. And I'd like to spend a little bit of time to talk about these modular graph functions, because that's the reason I have been working on these string amplitudes in the first place, because when I did my PhD, I liked a lot modular forms, and that's how I got involved in this whole business, because there are a lot of open questions about these modular functions. So let's start. So modular functions, of course, there will be functions of tau, and tau lives in the upper half plane, and you define lambda tau to be the lattice z plus tau z. And then you define functions associated to graphs in a rather cumbersome way. So I think it's better to first fix a graph and explain you how to associate the function to that graph, and then you can imagine how to do so in general. So the graph I fix is the following. You have two vertices and three edges between these two vertices, and I call this graph B3 because it's the banana graph 3. So maybe you don't see now why this is called the banana graph, but with B4 you will start seeing a bunch of bananas. So this is also called the sunset graph, because this looks like a sunset over the sea. And the function is defined in the following way. So you take, well, 3 copies of im tau over pi, which is due to the fact that you have 3 edges. And then the sum over 3 vectors in this lattice z plus tau z, omega 1, omega 2, omega 3. You want them to be different from 0. And you consider their inverse second power in the denominator. So you can think of all of these omega i's as associated to one of these edges. But then the numerator, this is related to the vertices. So as soon as in one vertex you have a few edges going in, then you consider the delta function of the sum of the edges going in, which are given by these vectors. So when I say delta of omega 1 plus omega 2 plus omega 3, this is some kind of momentum conservation of the edges that enter into a certain vertex. You should write 2 of these conditions, so 1 for this vertex and 1 for this other vertex, but they're exactly the same conditions, so I only write 1. And in the exact same way, you define modular graph functions in general. But let me first stick with this one. So this one, one can see very easily that it's modular invariant, and it's not at all easy to see that it can be written in the following way. So this was shown by Donzaguier. So it can be written in terms of zeta 3 and in terms of E of 3 tau, where E of S tau is the real analytic Eisenstein series that you might, I mean, it's a very classical object defined in this way for complex S. And now we are specializing it for S equal 3. Okay, so we are finding something which is interesting but still classical. Let's see something else which is classical. So if you consider the graphs given by polygons like this with n vertices and just one loop, well, you apply the recipe I told you for this one. So you have one omega I for each edge, and then you have the momentum conservation at each vertex, which imply that omega 1 is equal to omega 2 is equal to omega 3, and so on. And so eventually you just have, suppose you have n edges, then you just have 1 omega to the power 2n. And this is precisely the definition of the non-holomorphic Eisenstein series. And so you get just on the nose, you just get E of n tau. Okay, but these are the only simple modular graph function, let's say. So they're the simplest ones, because as soon as you go a little further, so you have the banana graph B4 with 4 edges and 3 bananas. Well, you just write down the definition. It's the same as here, but now you have 4 edges. So you have these 4 contributions here. And well, you cannot write this in terms of real analytic Eisenstein series or other known functions in the literature. This is something new. And that's how mathematicians like Don Zagier, Francis Brown, and many others got interested in this business. So a little remark is that there are relations among modular graph functions. So the first one is the one found by Zagier, which can be rewritten in this form. So this is one graph, this is another graph, and then there is this zeta-3 coefficient. And there are also differential relations among modular graph functions. So this one, for instance, involves B4. So even though you cannot write B4 directly in terms of real analytic Eisenstein series, there is a differential equation in terms of the Laplacian that relates you d B4 to this d associated to the polygons, which are known functions. So there is this ring of modular graph functions which satisfy a lot of algebraic identities, a lot of differential identities, and people are studying all these identities. It's a very interesting structure, but I'm not going to talk about that at all. What I'd like to say instead is something about the asymptotic behavior at the cusp of modular graph function, because this is related to this period story that I was telling you. Okay, so first of all, the real analytic Eisenstein series E of n tau have a asymptotic expansion as q goes to 0, which is well known. So you have q to the m, q bar to the n. You have 2 pi imaginary part of tau. Oh, yeah, sure. So this is a Laurent polynomial in 2 pi imaginary part of tau, which depends on big N and then on m and n. And these Laurent polynomials, well, will have rational coefficients in general if mn are different from 0, 0. And there is actually an explicit formula for them. But in the 0, 0 case, you have a first coefficient which is rational, which is a Bernoulli number, but you also have an odd zeta value, so something which is non-trivial. And this property of real analytic Eisenstein series, it generalizes to all modular graph functions and gives very interesting asymptotic expansions. So this is what I've studied in my PhD thesis. So you can prove, so this is combining a theorem of my thesis with a refinement by Eric Panzer in 2018. You can prove that your modular graph function always has an expansion of this kind, like the one of real analytic Eisenstein series, where the coefficients here are Laurent series with multiple zeta value coefficients. So this Z is the Q algebra of multiple zeta values. So this is coherent with what we have found here, but it's telling you that in principle you can have more complicated multiple zeta values, and indeed you get more complicated multiple zeta values. In fact, you get, if you do some experiments, as I did in my thesis, you find only single value multiple zeta values, and the first irreducible one starts appearing with 7 edges. So it's already some quite non-trivial modular graph function. And due to these computations, we conjecture that there is only single-valued multiple zeta values showing up. And yes?
Is there a condition or a hypothesis on the graph in this result?
Okay, so the graph don't have self-edges. So you never consider graphs which only have one edge between two vertices. I'm sorry, that's not correct. No, I think that's the only condition, that you don't have self-edges. And you can have multiple edges between the vertices.
Okay, thanks.
And, well, okay, so as I said, there are no self-edges, so the only two vertex graphs that are possible are those given by this banana family with n edges between these two vertices. And we have proven with Don Zagier, and then there is also another proof by Eric Docker and Michael Green, that this conjecture is true for all these graphs. But this is just the simplest kind of graphs that you can consider in some sense. Okay, the simplest graphs are the polygon graphs, but these are just the two vertex graphs. And for already three vertices, you can get, as I say here, all kinds of complicated multiple zeta values and don't have any control of them. So another remarkable thing is that in the two vertex case, and we have proved that, you don't get, we proved that you never get this kind of objects, you just get odd Riemann zetas. Okay, so this is some overview of what is known, but what are the periods behind all this? So I will conclude my talk by telling you about this and telling you then what is going to happen or what is supposed to happen in higher genus. So the mathematical framework is that of periods of fundamental groups. So let us consider a smooth complex manifold M, and if you consider the singular homology, you all know that this is essentially the abelianization of the fundamental group of the manifold at any point x. And well, this is not quite correct. I'm sorry for that. If you tensor this with Q, this is isomorphic to the quotient of the group ring over Q generated by the fundamental group, quotient by the second power of the augmentation ideal. And where the augmentation ideal is just this kernel, which sends you a linear combination, a formal linear combination with rational coefficients of loops to just the sum of the coefficients. And if you pose the same the following problem, you look for functions on the group ring Q pi 1, which are homotopy functionals, therefore. Well, you're kind of asking of generalizing the problem of looking for functionals on the homology group, because I mean, this is in some sense a quotient of this group, but you would like to consider the whole group ring. And the idea, as you do with the singular homology, is to use integrals. So what do you do here? You use differential forms and the Durand theorem, and you can describe all of the functionals with just integrals. But if you try to do so for the fundamental group, well, you run into an obstacle, which is the following fact. So suppose you have a smooth one form, and you want to do the integral of this one form. Well, this is a homotopy functional, so it defines a function on this ring, if and only if your form is closed. But if your form is closed, then it can only detect element in H1 in the abelianization of your fundamental group, because well, that's the Durand's theorem. I mean, if you have some element in here in the fundamental group which vanishes in the abelianization, then the integral of omega over that element will also vanish. I mean, if you want, this is a consequence of Stokes. And the solution by Chen to describe the homotopy functional is to use iterated integrals. So instead of integrating one form, instead of considering these line integrals, you give yourself R smooth one forms. And if this integral is a homotopy functional, then you can prove that it defines a function on q pi 1 over the augmentation ideal to the r plus 1, not just to the second power, but to the r plus 1 power. And this is in general non-trivial for the rth power. I mean, for any power up to r plus up to r. So this is one way to find functions that detect elements which vanish in the abelianization of the fundamental group. And Chen used it to, in fact, describe all the functions on this kind of quotients. I mean, it took the inverse limit of this quotient, and these are just the functions on the pro-unipotent completion of the fundamental group of your smooth manifold. And he proved that in some sense, I mean, there is some way to make this more formal, but you can consider a space which gives you all the homotopy invariant iterated integrals. And this is isomorphic to the ring of functions, so your homotopy functionals, the ring of functions on the completion of the fundamental group after you tensor with C. So this is some kind of analog of the Ram theorem, because as I said, P1 generalizes H1. And for this reason, people call them periods of pi 1, unipotent. This is not quite correct because this is not the analog of the Grothendieck-de Ram theorem, it's just the analog of the de Ram theorem, but when you give yourself an algebraic setting, then you indeed get numbers that are periods in the usual sense. And also let me remark that there is a relative version, which we will use for the fundamental torsors of paths from X to Y. Now, what does this have to do with what we did so far? Well, first of all, let me remind you how to compute in practice this kind of homotopy invariant iterated integrals over a manifold. So you have to use a model of your complex or smooth differential forms. Otherwise, this is quite hopeless because you would have to look at all possible iterated integrals of smooth forms and look at the homotopy invariance. This is very complicated. But if you use a model of your complex of differential forms, which is simple, then it's simple to look at all the iterated integrals. And a theorem of Chen tells you that you get exactly the same functionals. So you can use the model. And it's not difficult to see that a model for P1C minus 0, 1 infinity is given by the following DGA. So this is in degree 0, you just have the rationals, and in degree 1, you have q dz over z plus q dz over z minus 1. So this is a quasi-isomorphism with the DGA of differential forms of P1C. And this gives you the fact by Chen's theorem that the functions on P1C are homotopy invariant iterated integrals of dz over z and dz over z minus 1, because they are the only forms that appear. Okay, they are automatically homotopy invariant because these are holomorphic forms. So just any kind of iterated integrals which is convergent of these forms will give you a homotopy functional and describe therefore all the periods of the fundamental group of this manifold. But we have seen that multiple zeta values are given by this kind of iterated integrals, and in fact all such iterated integrals give you multiple zeta values, and therefore multiple zeta values are the periods of the pro-unipotent completion of the Riemann sphere, minus 3 points. And this is a genus 0 Riemann surface. This is in fact the prototype of genus 0 Riemann surface, and that's why multiple zeta values are very much related with genus 0 Riemann surfaces. And it was proven by Brown and Levin in 2011 that you can construct a model for a rational model for an elliptic curve minus the origin, and compute using this model all the periods of the pro-unipotent completion of this elliptic curve. And and it turns out that all the periods are given by what I've defined as elliptic multiple zeta values. This tells you that elliptic multiple zeta values are indeed the correct generalization of multiple zeta values in genus 1 in this setting. So this is how you associate a genus to all these numbers, and this is also how you think of elliptic multiple zeta values as periods. Okay, good. Now we have some kind of period viewpoint on these elliptic multiple zeta values, and therefore on the genus 1 string amplitudes. And what is the expectation of people is that at genus 1, these closed string amplitudes is the single-valued analog of the open string amplitudes, where the open string amplitudes is given by some periods of a fundamental group. So you have this single-valued machinery, and you should be able to apply this to a motivic version of this open string amplitude to obtain a single-valued closed string amplitude. But this is very vague, of course. What is more concrete is the following fact. So Francis Brown in 2017 used his theory of single-valued periods to construct a class of real analytic modular forms which are single-valued analogs of the elliptic multiple zeta values, and whose asymptotic expansion he proved to be constituted by single-valued multiple zeta values. So this guy look exactly like the modular graph functions that you find in closed string theory, and they come from elliptic multiple zeta values, which are the guys you have in open string theory. And so, of course, this seems to have to do with this expectation. And the conjecture is that, indeed, modular graph functions should belong to this class constructed by Francis Brown. And a conjecture 2, which is, in fact, very much related with conjecture 1, but is due to physicists and is related to some observation of the physicists, is that if you just look at the asymptotic expansion of the modular graph functions, then you can obtain this asymptotic expansion from some open string analog of these functions, which are therefore some elliptic multiple zeta values, in a very concrete way. You just apply term by term the single-valued map from genus 0. So you have, whenever you have a multiple zeta value, you transform that to a single-valued multiple zeta value, and that's it. And quite incredibly, this genus 0 version of the story seems to work very good. So it's an open conjecture also. And with Donzaghir, we proved this conjecture, again, only in the case of graphs with 2 vertices, so these banana graphs. But conjecture 2 is open in general, and conjecture 1 is open in general. And so there's already many open problems in genus 1. There's this very fascinating structure. But of course, physicists like to think that the problem is already solved as soon as you have understood how the things work and you have a conjecture. And so they looked at higher genus. And so let me just conclude with the last slide about future directions in higher genus. Because in the closed string case, Eric Docker, Michael Green, and Boris Piolin have constructed higher genus analogs of modular graph functions, which are Siegel modular functions, which compute the coefficients of closed string integrands in genus 2 with n points, and they're conjectured to compute the higher genus string coefficient 2, but they can, I think they can show this only for g equal 2 for the moment. And special cases of these new functions they constructed are known from Arakelov geometry and are called the Jean-Cavazumi invariants. And they're very interesting functions by themselves, but they're just the simplest special cases of this new class of modular graph functions in higher genus. And in the open string case, nothing is known in higher genus. Let me also mention that. And what is the expectation the expectation is to find, in general, both in open and closed strings, to find periods of pro-unipotent completions of higher genus Riemann surfaces, as you do find in genus 0 and genus 1, and that the closed string periods, so the periods in the closed string case, are the single-valued analog of the open string periods, as we have seen in genus 0 and conjecturally in genus 1. But it's still an open problem to construct these periods of the pro-unipotent completion of higher genus Riemann surfaces. And so that's where the math fails to support the physics. But essentially, all of the mathematical structure of string amplitudes was built after physicists have noticed that there was some interesting structure. So mathematics is kind of following the physics. And I hope soon we will be able to answer to this question. And I am personally working on this at the moment with Benjamin Enriquez. Okay, so I'll stop here. Thank you very much. And sorry for the delay.
Thank you. All right, so do we have questions for Federico?
Federico, at some point you write this differential equation with the Laplacian involved.
Yes.
Well, I think one can prove it mathematically, but usually physicists, they prove this kind of things going back to this Feynman integral and this graph stuff. They make the justification of this kind of differential equation in terms of manipulations of graphs and so on. Is this the case, or this is just like Zagier sitting down and they're verifying the equation?
No, they demonstrated the equation mathematically. So it's so they found a lot of these equations just by looking at the asymptotic expansions and trying to match the asymptotic expansions, and they put out a lot of conjectures of this kind. But then they were also able to prove many of these conjectures. So it's not so this is demonstrated, and many others. There are even infinite families of differential relations which are demonstrated in some nice articles by Eric Docker and collaborators.
Something also, is it possible to verify this, your conjecture experimentally, in the sense that taking a graph, trying to write down the expansion, trying to find out the values of zeta which pop up there, and is it done, or it is possible to do?
Yeah, all of these conjectures that are mentioned here are justified by these explicit computations that were done by physicists, and then in my thesis I developed an algorithm to do it to higher number of points for the graphs, and verifying this for very complicated graphs gave a pretty convincing hope that these conjectures are true. But there is also the fact that they are justified by analogy with the genus 0 case, and so there is some geometric reasoning behind all this.
Okay, maybe I stop recording and then we, Thiago,
yeah.
you ask.